Hello again. Welcome to my video on arithmetic series and the start of our series unit. I'll be going through the notes that the handout here, so if you don't have one of these, you might want to get it. Before I get started, I'm just going to apologize in advance if this video is not up to the quality or lack thereof of some of my other videos. I'm exhausted, so like not punch drunk, stupid exhausted, like gonna fall asleep exhausted. So if there's really long periods of no sound, it's probably because I passed out. We're gonna try this though. That, and I'm also, okay, here's an Arthur Does Rants, like some people have been asking for. Also, I just discovered that someone decided to etch hi into my window at some point during the day, and that's really bugging me actually, and it's not gonna come out. So yeah, super happy. But I don't mind doing the video. I'm not upset about doing the video. So yeah, let's get started. First thing, you might have heard me say it at the beginning. These are called arithmetic series, not arithmetic series. Words, yeah. Funny things. But the adjective form of arithmetic is said arithmetic. So before we talk about series, though, we need to start talking about sequences. I'm going to go through this fairly quickly, the stuff that's been written. I'll work the examples. Oh, and I've had some, not really complaints, but requests about keeping things a little bit shorter. So I'm going to set a timer for 20 minutes. Yep, this thing right here. And we're going to see if I can do it. Okay, we'll see how that goes. Anyway, all right. First thing we have to talk about is sequences. So a sequence is a list of terms in a specified order. Okay, we use this notation here. Usually we'll use A to represent a term, and we use subscripts to represent their position in the line. And so since they have an order, A sub 1 is always the first term, A sub 2 is always the second term. And then we use A sub n to represent the last term, okay, if it's a finite sequence. If it's infinite, it just goes on forever. So as you can see here, we have a finite sequence. Okay, another weird word. We say infinite, but we say finite, not finite. Go figure. A finite sequence has a first term and a last term. It ends. An infinite sequence goes on forever. And a sequence has a rule that defines it, whether maybe we're going up by 1 or 2 or multiplying by a number. There's always a rule that defines them. So oftentimes the terms in a sequence will have a pattern. We can represent these patterns with an equation. So first thing I want to talk about is pattern recognition. So here's a sequence here: 1, 1/4, 1/9, 1/16, and we want to write out an equation that we could use to model this. Okay, so I need to rewrite these terms for a second here. 1, 1/4, 1/9, and 1/16. Okay, we want to write an equation that relates their position in the sequence to their value. So, obviously here's my first term, second term, third term, fourth term, and so on and so forth. Okay. When approaching these, it's always a good idea to see if you can predict the next term. Okay, if you can, that generally means you recognize the pattern. Another hint that I want to give you is that anytime you come across a combination of whole numbers and rational numbers, you want to make that whole number, it's a different color, into a rational. Okay, it just helps you see the pattern. So this is the same as 1/1. Any whole number just over 1. Okay, so my second tip is that we treat the numerators and denominators as a separate series or sequence of numbers. Okay, meaning I'm going to ignore the denominators. I'm going to look for a pattern in the numerators, which is pretty tricky, but if you think about it hard enough, I'm pretty sure you can see the pattern of always 1. And then our denominators we'll look at separately, the 1, 4, 9, 16, and find their pattern. Okay, so I'm noticing with my denominators, though, that these are all perfect squares. Okay, so this is like 1 squared. Here I have 2 squared, 3 squared, 4 squared, and that's sufficient evidence to convince me that they would continue in that manner. So notice that what's being squared relates to the position of the term. So let's replace, since we want to talk about any position, let's replace the position with just an x. Okay? And since the numerator is always constant at 1, I know I can do a function of 1 over x squared, where x is the position. Now we also want to graph this, but we need to pay careful attention to where this is starting. Okay? X tends to be a continuous variable, meaning it can take on any value from negative infinity to infinity. But here we have a starting value at 1, and since that's my first position and we're not given any evidence to suppose that we're going to go negative, we need to put a little restriction, so I'm drawing this, on our function. We want this, and we also need x to be greater than or equal to 1. Okay. It's okay if x were less, but just not for this sequence. Others may go negative, and that's fine. You'll start it so that your first x value gives you your first sequence term. Okay. So this one's actually really hard to graph because we start at, let's go green. We start at 1 comma 1. When x is 1, the value of this fraction is 1. When x is 2, the value of the sequence is 1/4. So, yeah, good luck putting that one in there. And then 1/9 at 3, yeah, and 1/16 at 4. So, this thing when you graph it, it's not the best. Keep in mind though, it's never going to touch 0. Okay, even if you do 1 million squared, it's tiny, but it's still not 0. So there's that graph, and we would leave it just like that. I apologize to anyone who was in my second period class. I graphed the full function, and that was a mistake that I realized a little too late. So there's that. Okay, before I read this paragraph, I want to talk about then the difference between a sequence and a series. A series is the sum of the terms in a sequence. So we're adding them up. Okay. Sorry, I had to check a text message. So there are two types of series and sequences, technically, that we can talk about. So if the sequence has what's called a common difference, it's an arithmetic sequence. So a common difference means that we are adding or subtracting the same thing to get the next term. Okay, I'm going to squeeze an example here in just a second. And then a geometric series, on the other hand, has what we call a common ratio, and that goes with multiplication. Okay, so we're multiplying by the same thing each time. Let's look. Okay. Arithmetic sequence or series. Call that AS. Okay. So this thing has a common difference. Which goes with addition. So the questions come up, though, so can we ever have subtraction? And you absolutely can, because that's just like adding a negative. So we say everything's with addition, but you know, technically you can get into the subtraction realm. So here's an example of an arithmetic. Let's go with series, because that's the main focus here. If I do 3 plus 6 plus 9 plus 12 plus blah blah blah, okay, you'll notice that each term is going up by 3, and so my common difference is plus 3 for each time. Now, geometric series, on the other hand, call that GS, has a common ratio which goes with multiplication, and so an example of that, also using 3, these things get big really fast, so we have 3 plus 9 plus 27 plus 81 plus so on and so forth. Okay, so I'm still adding them up. Alright, I never stop adding things up for series, but the way I get each term is I'm multiplying the previous term by 3 instead of adding. So times 3. Okay, Geometric series will be the focus of my next video and the next notes. So we're going to focus on arithmetic series today. So there's some notation that we need to go over here. So this is sigma, okay? Capital Greek letter sigma. In the math world, it means that we are summing things up. It's also called summation notation. I think your homework uses that a little bit. So when we do sigma notation, we always need a lower limit, or where we're starting from. We're always using an upper limit and then an explicit formula. Now, the thing about series, though, is that we only count in whole numbers. So we always use this variable k. We don't use x anymore because x is continuous. Okay? I always like to say k for counting because that's how mathematicians spell. I'm going to write that. K for counting. That just looks terrible. But that's to help you remember that k is only the numbers you might count. Could be the integers. I mean, technically we could go negative, like -2, -1, 0, and then 1, 2, 3, 4 on up. Okay, but no decimals, no fractions. All right. So n is our upper limit. That tells us where we stop with k. And when I start to do an example, it might make a little more sense. The other thing that I do want you to write down, though, is that this n can also tell you the number of terms in your series with one condition. So also the number of terms if, like, this is super important, like triple underline important, if k starts at 1. Alright, that'll become clear in just a minute. Alright, so let's look at how we use these things, and we'll flip over to the next set. Oh, nope, I did it again. Okay, every class I've forgotten this. I want us to tell you how we say this so we can sound intelligent when we talk about them. Okay, so if I wanted to describe this, I would say that this is the sum from k equals 1 to n of 2k plus 1. So the sum of nope. Oh my goodness. Okay. Pretend that didn't happen. Okay, the sum from k equals 1 to n of 2k plus 1. That's how you'd say that. Okay? So now let's go to the back. How am I doing for time? Terrible. 12 minutes. 1 page. What the heck? Alright. We're in for a long night. So, write out and evaluate each sum. So, if any of you have done any programming, I like to think of summations as loops, especially for loops, okay, and where you have an iterator or a counter as you go. So, one way to look at this is to say, okay, here's my formula, k to the third, and I'm starting with k equals 3. So the first term that I write is going to be 3 to the third power. Now I'm done with k equals 3, so I step up to the next k value. So I step to 4, and my sigma tells me I'm adding them up. So I'm at 4 to the third, and then 5 to the third, 6 to the third, and finally 7 to the third. And that's where it tells me to stop. Once I get to 7, my upper limit, I'm done. And it wants me to add all these up. The weird thing is this whole sigma notation stuff, all these that you see, is actually just a number. They represent one single number. Okay? So this number happens to be, looking at the magical cheat sheet, 775 when you add these all up. Okay? Yes, there is a way to do that in your calculator faster. Have fun figuring it out. You can Google it. But there's also a formula that we'll get to at the very end that will save us a lot of time as well. All right, so next one. Let's go with this one. So I'm going to start at k equals 1. So I'm going to do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And when you add all that up, it's 55. Now I want to do both of these so that I can go back to that note that I said where the upper limit can tell you the number of terms if k equals 1. Okay? Notice that both of these add up 5 terms. Okay, they add up the same number of terms. In example B, my upper limit was 5. So that's nice. But in example A, the upper limit was 7. One of the common mistakes that students make is that they assume that the upper limit is always the same, is always the number of terms. And that is not the case. It's only the case if k equals 1. Okay? The other thing that then they assume is they might remember that, but then they say, oh, well, I need to figure out how many terms there are without writing them all out, because maybe you went up to 1,000. Okay, you started at k equals 42 and you went up to 1,000. You really don't want to write out all those 900 and something terms. Okay? So a lot of times we want to just subtract. We say, okay, well, there's a 7 minus a 3, and that would give me 4, but we know right here, we have evidence to support that that doesn't work either. Okay? So we've got to be careful. Just a quick diagram to show you what's going on. If I have 5 things, dots, no, 7 dots, let's say that. 1, 2, 3, 4, 5, 6, 7. Okay? And I want to start at the third one. Okay, I want these ones. That's ridiculous. Who counts from the left? Whatever, apparently I'm counting from the left today, so that's the third term, and that's the rest of them. Okay, I want to start at the third and go to the seventh, which gives me 5 terms. If I just use subtraction and I subtract 3, that means I'm taking away 3, which only leaves me with 4. So sigma notation is saying something a little bit different than just regular subtraction. Okay? So be careful of that. The general rule is you can subtract the lower limit from the upper limit and then just add one more for the endpoint. Okay? And you'll see you will need to know how many terms are in a series for the formula that we're going to get to at the end. So it is important. The rest of these, I feel like you can figure out C, honestly. And just know that when there are multiple k terms, that you just plug in k for all of them. So this is 1 over 1 plus 1, and then I'm going to add 2 over 2 plus 1, and I'm going to add 3 over 3 plus 1, and finally 4 over 4 plus 1. Okay, fractions are okay, and so you get 163 over 60. So sometimes we assume that since k is always a whole number, that our answers have to be whole numbers, and that's not true either. Your formula can give you fractions all the time, and so that's fine. We're just counting with k's, and this is not a 1. That's a 1. Ta-da! Alright, moving on. How am I doing with time? You can't even see that. 3 minutes. Not going to happen. Sorry. Alright. So sometimes we're asked to go backwards. Sometimes we're given a series of numbers and asked to write it in sigma notation, to shorten it down. A lot of times, like this one here, there's this whole dot 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 in the middle, which says the pattern continues until you get to this value. Okay, so it could be a really long series of numbers that we want to shorten with sigma notation. Okay, I have to make a note here. This reminder from secondary 1, haven't used that in a long time. If that makes sense to you, go for it. I mean, it makes sense to me, but it's nothing that I plan on using. So that's what you get when you steal other people's notes with their permission. It's not stealing. All right, so let's start with the basics. What we know every time, we've got to have a sigma. Okay. Now, I want to go on my sigma rant, but I'm running out of time, so I won't. But this symbol bugs me, and don't worry if yours are kind of not straight like mine normally are. Okay, this goes back to pattern recognition though. There are some things that we can see being constant. Hopefully we can identify a pattern in the denominator as well. But I want to talk about the limits first. So I really want you guys to get in the habit of starting at k equals 1. There are an infinite number of ways to write a sigma notation for any given series. Okay, but the ones that we're most interested in start at k equals 1. So that's the goal. So upper limit, let's come back to that for a second. Let's make the explicit formula now. Since the numerator is constant, I know that I'm going to have a 1 up there. And then I want you to pay attention to what we're changing by every time. Let's look at the denominator. We're changing by 1 each time. So that common difference is always going to be a multiplier for my k values. Okay? So technically I want to have this 1k down here. If I was changing by 2 each time, this would be a 2k. If it was 3 each time, it would be a 3k. All right. I want to go more in depth than that, but I want to do it on the next one. So we'll go here. Now, we need to make sure that when k equals 1, I get a 1/3 out of this formula. Okay, the way it sits right now, if I plug in k equals 1, I get 1 over 1, which is just 1, and that's a problem. So let's think, what do I need to add when k equals 1 to get to a 3? Well, I need to add 2 more, right? So now when k equals 1, 1 plus 2 is 3, and I get 1/3. Okay, let's check the next term. When k equals 2, so my second term, 2 plus 2 is 4, I get 1/4. Perfect. All right, I'm there. Now let's talk about the upper limit. I know this is my last term right here. So what does k need to be? Oh, be quiet. That wasn't 20 minutes. You cheated. Somehow my timer cheated. All right, back to this one. When I have 10 in the denominator, what does k need to be? Well, k would need to be 8. 8 plus 2 is 10. So that means that my upper limit, as well as the number of terms I'm adding up, is 8. Now, you might be tempted to take the easy road, which is great. It still works. There's maybe an easier way to do this if I did sigma, and I said, oh, well, let's just do 1 over k for my formula, and why don't we start at 3? That's 1/3, and then I just need to go up to 10, and there's sigma notation. And you know what? These are give you the exact same thing. Okay, they're going to generate the same series of numbers, but this one gives us less useful information than this one. And I know I keep telling you to wait, and it's coming, I promise, why this is more important. But we are going to push for k equals 1 on all of these. Okay, so it's red. It's important. Alright, go over here. Alright, so next series that we've got, a lot of times you'll see me draw this to find the difference. These are going up by 6, by 6, and we're given to imply that that pattern continues on up to 72. Now, I want you to think, every time I go up I'm adding a 6, but if I go up 2 spaces from where I start, I'm adding 2 6s. Okay, if I went up 3 spaces, I would be adding 3 6s. So we have a shortcut for repeated addition, right? It's called multiplication. So that's why for every one that I go up, I need to multiply by 6. Okay, if I move 1 space, I've added 1 6. If I move 2 spaces, I've moved 2 6s, which is just like 2 times 6. If I move up 3 spaces, okay, I've added 6 plus 6 plus 6, which is like 3 times 6. So I just want you to start understanding that the common difference is always the multiplier of your k values. Alright? Now, I want to get in the habit of starting at k equals 1. Okay, we could easily start this at k equals 2, and then life would be grand and happy and fun until later. So, but we're not like that. We do hard things. So let's think, when k equals 1, I need to get a 12. So right now, if k equals 1, I get a 6. So what do I need to add to that to make it 12? Well, I need to add a 6 to it. Okay? So 6 times 1 is 6, plus 6 is 12. Let's check the next one. If k is 2, so 6 times 2 is 12, plus 6 is 18. Alright, this looks like it's going to work pretty well. So then finally, how do I get up to 72 though? How do I know how many terms I need? Well, we need to figure out what k is. So you might come over to the side and do a little bit of scratch work and say, alright, if I have 6k plus 6 equals 72, what does k need to be? Well, that's simple. Let's subtract 6. 6k equals 66. We can divide by 6, and I get that k equals 11. So I need my upper limit to be 11, which also tells me that there are 11 terms happening here. And there's my answer. Alright, back to something I said earlier, it is okay to do subtraction. You'll notice in example C that I'm going down by 2 every time, which is like adding a negative. So let's throw a sigma in here. If you watch this video and want to hear my sigma rant later, you should just mention it to me in class. I'll go on my sigma rant. So this is going to be my multiplier. Now, since I'm multiplying by -2, everybody just thinks it's nicer if you put that on the end. Like, for some reason, our brains are trained that we like the first term to be positive. And so I'm leaving a blank here because I'm going to be subtracting from something. You could put -2k first and then add, but I just know that no one likes that, including me. So I'm not going to do it because it's my video, and I'll do what I want in my video. So there. Start at k equals 1. And let's think. Alright, if k equals 1, that means I'm subtracting 2. What value minus 2 gives me 50? 52. Okay, let's check the next one. When k is 2, I end up subtracting 4. 52 minus 4 is 48. Okay, I'm convinced we're good. So now again, how do we figure out how we get to 30? You can do the same trick that we did up there, or one thing, just a little mental trick. What do I have to subtract from 52 to get 30? Well, I need to subtract 22. So I need my 2k to equal 22. 2k equals 22, divide by 2, divide by 2. So once again, I find that k is equal to 11. And so I have 11 terms. Alright, any questions? Of course not. You're not in front of me. Yeah, we're done. Okay, so finally, let's get to the end. There is a shortcut to adding up series. Like I mentioned earlier, maybe you have a series of 1,000 terms, and that is cruel and unusual torture to have someone just write that out. Okay, so what if we want to add them up though? We need to know what's going on. Well, there is there's a formula for the sum of a finite arithmetic series. Alright, there's actually 2 of them, and you'll see them here in your notes. This first one is the only one that I use. I honestly forgot this one existed till I saw these notes. Doesn't mean it's bad. It does work. I can break it down for you at some point, but I've never found a need to memorize both of them. And so we're going to stick with the first one. Now, you will notice that it lays out what each thing is. So A1 is the first term, and colors are fun. A sub n is the last term. N is the number of terms. And D is the common difference that's not used in our formula. It's used in the second one. But just good to know. Now, this is where we need to know n is the number of terms. I know at the beginning, come back, that we put an n here. Alright, that n is the same n for our formula so long as k equals 1. Otherwise it's not. So, we use a capital S to represent the sum. Alright, so this is the sum. Now, we need to figure out how many terms we have. That's probably the first thing to do. Well, no, it's not. Come back to that. So I'm going to do the number of terms divided by 2. It's always divided by 2. Okay. Times, now it's really easy to see the first term. Okay. Here's the first term. It's -5. here's the last term. It's negative 71. Now, it's always plus, okay, but it's okay to add a negative. So plus a negative 71, which, yes, comes out to be subtraction. Excuse me. Okay, so now we got to find this n. So the best way that I can suggest to do this is actually to turn it into sigma notation, the way that we've been doing. So I notice that there's a pattern of of negative 6, so I'm going down by 6 every time. So I know that I'm going to subtract 6k. I know that I want to start at k equals 1. Alright, to make my first term work, when k is 1 and I'm just subtracting 6, what do I need to subtract from to get me a negative 5? Well, that'd be 1. 1 minus 6 is negative 5. Alright, so then I can take, like I did above, and I can set 1 minus 6k equal to negative 71 and solve. Alright, so 1 minus 6k equals 71. Minus 1, oh, negative 71, sorry. So negative 6k equals negative 72. Divide by negative 6, and you get k is equal to 12. Okay. So that means that my upper limit here is 12, and therefore the number of terms that I have is also 12. So much for my color coding. Come back. There we go. Alright, now this is something you're just going to type into your calculator. Please make sure if you choose to just type it in as is that you put parentheses around it, or you can do some simplification on your own. So this is 6 times negative 76, and we get the sum of the first 12 terms. That little 12 subscript is just to tell you how many terms you're adding up. Okay, is equal to negative 456. Alright, clear as mud. Good, moving on. Last one. Okay, now I find when you have sigma notation, it's actually a little bit easier to do, especially if we start with k equals 1. So I want the sum of the first of my 8 terms, okay, is equal to 8 over 2 times, now finding the first and the last term, it's not right there in front of your face, but it's just one step away. To find the first term, I'm going to plug in k equals 1. Okay, so 4 times 1 plus 3 gives me 7. So that's my first term, a sub 1. My last term is when I plug in 8. 4 times 8 plus 3, so that's 32, 35 equals 35. And that's my last term. Alright, so put those into the formula. I get 7 plus 35. And I can simplify this down for a little bit. Equals 4 times 42. So the sum of my 8 terms is equal to 168. And there you have it. Arithmetic series. Some people ask, how come we don't have a sum for an infinite arithmetic series? And to those people, I just slow blink a little bit and move on. Think about it. Okay, just think about it. Other than that, with series, there's a lot of variability. I know I went a little quick, and I want you to focus on getting k equals 1. But there are lots of different ways you can do this. So if you end up with a different answer than your friend, doesn't mean you're both wrong. It could mean that you just have different versions. Other than that, I apologize about very few jokes. I did have a joke prepared about good series and bad series, and how like good series are like Big Bang Theory and bad series are like Twilight or something like that, but didn't quite pan out, so sorry about that. Hopefully the next one's better. Hopefully that made some sense, and I'll see you next time. Bye.